Hi guys and welcome to this video. Today I want to talk about tapered threads. I've been asked how one would model these in Fusion, so I decided to do a quick demonstration. Tapered threads are commonly used in pipe connections for the sealing properties. These threads provide relatively leak-proof connections, but also are mechanically strong. In the context of 3D printing, they allow to tightly mount parts without having inner tension in the threaded section, which is not the case for conventional cylindrical threads. I quickly sketched the difference. In the cylindrically threaded design on the left side, the inner part is under axial tensile load, which is typically bad for 3D printed parts, assuming horizontal layer orientation. The tapered threaded part does not suffer from this effect, as the loading is effectively applied in the radial direction. The method I'm going to show is somewhat different from what I've demonstrated in my other videos on custom threads, so feel free to watch them afterwards for choosing your preferred method. But without any further ado, let's get into designing. I start by creating a sketch on the front plane. In this sketch I will define the thread profile and the taper angle. I start with a quadrilateral shape. Here already I use the buttons on the right side to make the left line a center line and the top and bottom construction lines. Then I define the lower diameter as 30 mm, which will give the larger diameter of the thread. Next I define the taper angle. Commonly used tapered threads have very low taper angles. For such a thread I would enter a value below 1 degree. However, for this example I chose an angle of 5 degrees. Unfortunately, angular dimensions get moved quite a bit sometimes, so I return it to where it belongs. The height of this shape does not matter at all, as we will see later. I make it 10 mm. Next, I lay out the thread profile. By dragging while holding the mouse button, I create an arc while using the line tool. I found that filleting the thread profile afterwards did not work properly, so I included this in the sketch. Next, I make the inner line parallel to the taper line. Also, I make the arc center coincident to the outer corner. Next, I specify the fillet radius at 0.6 mm and the flank angle at 90 degrees. Also, I set the height of the profile to 1.5 mm, but we will see that this value will not matter much in a minute. Now we can see that there is still 1 degree of freedom to constrain. For that, I add another construction line, connecting the arc center to the midpoint of the base of the profile. Then I make this construction line perpendicular to the taper line, effectively creating a symmetry constraint. This next step is not strictly necessary, but I want to check how this profile works with the pitch I'm going to use. So I select the profile by double-clicking and hit Ctrl+C, Ctrl+V to make a copy. I drag this copy to the approximate location where the next turn should be. Then I convert this second profile to construction lines. After constraining the center of the arc to the taper line, I add a dimension for the pitch, which I set to 3 mm. As you can see, the profiles overlap, which is intended in this case. Really, the depth of the profile does not matter, except that it should overlap when offset by the pitch, so I decided to reduce it a bit. Then I finish the sketch. The next step is to create the guide curve. This will be a tapered coil, which will be created in 2 steps. First, we create a solid coil based on the top plane and I enter the reference diameter of 30 mm. I want to specify height and pitch. The height should be sufficiently greater than the height of the threaded section I'm going to create. I enter 20 mm and the pitch value of 3 mm I also just have used in the sketch. The size of the profile has to be smaller than the pitch, so I set it to 2 mm. The exact value does not matter much, but we will need to use it again in a minute. Of course, we could and maybe should define parameters for the pitch and profile size here, but I did not, to keep it simple in this video. We want the square profile, the reason for which will become clear in a second, and we confirm the coil. Next, I extend the body inwards, as what we're really going for is just one helical face. So I choose press pull and select the inner cylindrical face of the coil. I extend it by 10 mm. Now I want to isolate the bottom face. One convenient way to do so in Fusion is to create an offset face with an offset value of 0. So I go to the Surface tab and do that. I don't need the solid body, so I remove it. Next, I want this face to start at the top plane. I choose Move from the Solid tab, select Translate and move it 1 mm, which is half the profile size, up in the Z direction. Now I use the taper line to create the cone. From the Surface tab again, I use Revolve for that. Now what I really need is the intersection curve of these two surface bodies. I can create this by splitting the helical face using the cone. So I select Split Body before selecting the bodies. I want the Extend Splitting Tool option to be checked. I really just need the inner remainder of the helical surface, so I remove the other two bodies. Now, finally, this outer edge is the guide I was going for. As we now have already completed the heavy lifting, feel free to like and subscribe and join my free community to ask your questions. Link in the description. I also enjoy reading feedback or ideas for new videos in the comments. Next, let's create the solid sweeping. Here it is important to uncheck the chain selection option before selecting the guide curve. Then I select the profile. I have to provide an orientation to keep the profile from rotating along the guide, so I select the Path and Guide Surface option. As guide surface, I could choose the helical surface itself, but the resulting body will be more efficient if I just use the top plane. I confirm the sweeping and now I can remove the helical surface. In case the sweeping gives you any troubles, you could try to alter the profile sketch as shown here. This will give the inner face a different topology and may avoid errors. Next, I want to create the fillet where the thread profiles intersect. I choose the same radius as with the outer fillets at 0.6 mm and confirm. I actually don't want to use the whole solid body, but only the outer faces. So I switch to the Surface tab and then remove the inner faces by just selecting them and hitting the Delete key. I also deleted these end faces, but these could have stayed without causing any issues. It might happen that the surface topology of your thread part is more complex, and it would be tedious to select all faces to remove. In this case, you could try to change the sketched profile as mentioned before. Another solution might be to create a new sketch and sketch a quadrilateral similar to the very first sketch, like shown here. Then you could create the revolute, which cuts away the inner topology as shown here, resulting in one single face to remove. Now that we have created the tapered thread as a surface body, we can go about designing the actual parts, which should interface using this thread. As a test part, I am going to design a simple disc with a threaded plug. For that, I create the sketch on the top plane and sketch out a 40 mm circle and a 7 mm hexagon, which I actually changed to 6.7 mm later before printing. In case you have not guessed the hexagon's purpose, bear with me for a minute. I'm not sure why, but the alignment constraint always gets lost with polygon shapes, so I recreate it. Then I just extrude the whole cylinder for 12 mm. Now we can see that the thread surface does not fully intersect the body I want to use it on. I would generally recommend to create the custom thread at the origin and move or copy it to the locations where it is actually needed. In this example, I just have to move the thread down a few millimeters. So I again choose Move and translate the surface body -5 mm along the Z direction. Then it is time to split the body. When selecting the tool surface, I strongly recommend selecting the whole body from the model tree on the left rather than just clicking it in the viewport. After splitting, I create a section analysis to clearly see the body's interface. In this case, offsetting the thread face using press-pull works fine. I enter -0.2 mm as offset and confirm. Oftentimes, however, this will not work on the finished solid part. What I would do in this case is to make an offset face based on the thread surface body and use this surface to make a separate split. This gives a separate body representing the clearance, which can subsequently be removed. Often, like with the pipe fitting I've shown in the beginning, we have two different bodies which will be cut using the thread surface. Let's have a look at the underlying sketch. Feel free to pause if you want to recreate it yourself. I started out with this revolute representing the inner threaded part. Then I split this body using the thread surface and removed the outer portion. Finally, I added the lower pipe part. Similarly, for the outer part, I started off with the threaded section like shown. I again split it using the thread surface and removed the unnecessary part before adding the main pipe body, ending up with this result. Back to my test part. Finally, I cut the hexagonal opening in the inner part. Its purpose is to fit the 1/4-inch hex bit commonly used as tool holder to tighten or remove the plug. As I have just recently calibrated my printer to give accurate dimensions while maintaining strong parts, which is a topic that definitely deserves its own video one day, I printed the version without any clearance. When printing threads, I always choose a random seam in this area to avoid any aligned seam stopping me when tightening. I found that I could tighten the connection to being almost flush, just to recognize that I was not able to disassemble it anymore. Only with the help of a lubricant and by forcing a larger Torx key in the center was I finally able to remove it again. I hope you found this video helpful or interesting. Feel free to like, subscribe, share and join. Links in the description. Have a great time designing and prototyping.